All right. In this video's lesson, what we're going to be talking about in section 1.5 is what are called dilations. What a dilation is it's a transformation that produces an image that's got the same shape, but a different size. In other words, you're making a shape either smaller or larger, but we're keeping the kind of general shape of it the exact same. So when we look at a dilation, we're going to have two different things called the pre-image and the image. So in the diagram over on the left side, so in the diagram right over here, your pre-image is going to be whichever one does not have the apostrophes after it. So that would be the triangle ABC. This is kind of your starting point. The second thing that we've got in that diagram over here is we've got a much larger triangle, which is called triangle A prime, B prime, C prime. And this is your ending image. So this is what it looks like after the dilation has occurred. So the question is a dilation an isometry? And an isometry basically means that the shape is going to look the exact same, it's just been moved. And the answer there is no, it's not. Either the angles or the sides, so the angles and sides are not going to be the same. Now, in a dilation, a figure is going to have one of two things. Either it's going to be enlarged, like the example we just got done looking at, and we're going to call that expanded is another way of saying that, or it's going to be reduced. In other words, it's going to be contracted. It's going to be a contraction, meaning it's going to look smaller. That's all going to be with respect to a fixed point, which we're going to call the center of the dilation. Now, as we talk about dilations, we're going to be talking about scale factors. And so scale factors are the ratio that compares the distance from the center of the dilation to the image and the distance from the center of the dilation to its pre-image. So when you find the scale factor, which we're going to call K, that's going to be found by taking the distance from your center to your image divided by your distance from the center to your pre-image. So K is going to be a fraction, unless it simplifies to be a whole number, but a lot of times we'll think about this ratio as being a fraction. So as a fraction, if K is a fraction between 0 and 1, then we're going to call that dilation a reduction. In other words, what a reduction looks like is you've got this kind of segment from your center, which we call O, up to some point P. And from that point P, we are making that segment smaller. We're moving it to P prime. And so that's going to end up being a K value, which is between 0 and 1, which is what this inequality right here says. Now, if K is a number that's greater than 1, then it's going to be an enlargement. Again, what that looks like is you may start with some form of a segment from O to P. And from that segment, we're going to enlarge it. We're going to make it larger. When we do that, that K value is going to be greater than 1, which is what this inequality right here says. So what exactly happens? Because there's a lot of terminology. What exactly does it look like? Here's an example. This dilation has a scale factor of 3 to 1. What that means is that our image is 3 times larger than our pre-image. Let's first compare our sides. So for our first side, we're going to compare A prime B prime to AB. Well, A prime B prime is this segment right here. So that had a length of 12. Whereas our pre-image, AB, had a length of 4. And so the ratio there of our two sides would be from 12 to 4, which if you wanted to, you could reduce that. 12 over 4 would reduce to be 3 over 1. And again, it said we get a scale factor of 3 over 1, so that should make a little bit of sense. All right, let's take a look at our next one. So let's now take a look at A prime C prime, which has this length of 15, compared to AC, which has this length of 5. Once again, when you compare 15 to 5, you can reduce that to being 3 to 1, and so it again follows that scale factor. Finally, let's compare B prime C prime, which has a length of 21, to BC, which has a length of 7. Once again, you can simplify that to become 3/1. What that really means is that the sides are not the same. However, the sides are proportional. Now let's compare our angles. Now, angle A and angle A prime are actually going to be congruent to each other, meaning that they've got the same measure. The same is true of angle B and angle B prime. And finally, the third angle is also true, which is that angle C is congruent to angle C prime. In other words, the angles are not proportional, but they are actually congruent, meaning that their angle measure is the same for both the image and the pre-image. All right, let's talk a little bit more about some of the properties of dilations and the notation that we use. So the following properties are preserved between the pre-image and its image. In other words, the following properties are always true. Your angle measure is always going to stay the same. So angle measure is preserved. The second thing that's going to be preserved is parallelism. So first we had angle measure, second is parallelism. Meaning that if things were parallel, if you had two lines that were parallel in your image or your pre-image, they are still parallel in your image. The third thing, which is preserved, is collinearity. What that means is that if points were on a line in your pre-image, they're still on the same line in your image. One important thing that's not preserved is distance. So distance is not preserved because if it was, we probably haven't changed much. And in that case, we really have kind of the same thing that we're looking at. So distance is not preserved. However, the distances will be proportional. As we saw in the previous example, the sides were proportional to each other. Okay, so some notation that we've got. We write that D sub O comma K of parentheses X comma Y is a dilation where O is the center of your dilation and K is the value of the scale factor. And then whatever is in the parentheses is your pre-image. And then if we write that as an equation, typically the other side of the equation is then your image. So let's do some practice finding scale factor. So on the next example, we're going to find the scale factor and determine the type of dilation. So we're going to do that for a few different examples. Let's start by looking at these figures that look kind of similar to kites. So looking at this first one, when we set up our scale factor, we're going to take our image, which would be from our center C to our P prime, so that would be a length of 5, divided by our distance from our center to the same point of our pre-image, so that would be from C to P, which is 10. And when you simplify 5 over 10, that is 1/2. That's your K value. Now in this case, K is a number between 0 and 1. What that tells you is that this is a reduction. Which should also make sense if you look at P going to P prime. That makes that distance from C a shorter distance. Let's take a look at another example. And this one's a little bit flipped. And so we're going to start by looking at our image, which means going from our center C to our point of our image, which is P prime. So that has a distance of 15. We're going to compare that to our distance between C and the same point of our pre-image, which was P, which was the number 7. So now 15 over 7, that's our K value. It doesn't reduce, we'll leave it as a fraction. In this particular example, K is greater than 1. If you take 15 and divide by 7, it's like 2 point something. And since K is greater than 1, we would call this an enlargement. Which, again, should also make sense. If you think about P as your starting point, going from P to P prime, you're getting further away from your center C, so you're enlarging your image. All right, let's do a little bit more practice deciding whether or not dilations are reductions or enlargements. And I've got them written in a bunch of different ways. So for example A, we've got our scale factor is 5/2. What that means is that k is equal to 5/2, which is a number that's larger than 1, in which case this is going to be an enlargement. For our next example, B, we aren't given any numbers, but we're told that here is our preimage A, and here's our preimage, or our image then B. So our preimage is A, our image is B. So going from triangle A to triangle B, we have gotten smaller. We're just going to have to do this one by looking at it. This would be an example of a reduction. For C, all we have to do is understand the notation to understand that the number 5 is our k value. That number is bigger than 1, so that would mean that this is an enlargement. All right, so for D, if we look at our distance from O to A, we're going from O to A, and we're increasing that to A prime. So since our image is larger than our pre-image, this would be an enlargement. Once again, example E just deals with notation, understanding that your k value in this case is 0.5. That is less than 1. So less than 1 would mean that this is a reduction. Lastly, for F, it tells us our scale factor is 2/3. Scale factor is just another way of saying your k value. In this case, k is a number less than 1, so this would be a reduction. All right, let's look at some more examples here. So we've got a dilation, which is centered at O. It has a scale factor of 3, and it tells us the length of our segments. OA is 6, as we see in the diagram, that OB is 7 centimeters, again, that's pictured for us, and AB is 8, again, that's pictured. So it wants us to find the measures of each of these other lengths. First off, it wants us to find this measure of A prime, B prime. Now, that's our image, which we're told a scale factor of 3 should be 3 times larger than our pre-image, which was AB. In other words, we need to take 3 multiplied by our length 8, tells us that A prime, B prime would have a length of 24. It next wants us to find O to B prime, so that would be this length here. Again, that's going to be 3 times longer than our pre-image, which was OB. Well, OB was 7, so if we take 3 multiplied by 7, tells us that our length is 21. Next, let's find O to A prime. O to A prime is going to be 3 times larger than O to A was, so that would be 3 times larger than 6, which is 18. Next, it wants us to find A to A prime, so it wants us to find this distance right here, which we know the full distance is 18 from O to A prime, but we don't want this piece right here, so we want less 6, and 18 minus 6 would tell us that that length would have to be 12. In a similar way, if we wanted to find from B to B prime, we know the entire distance from O to B prime is 21, but we don't want to include this 7, so we want to go less 7 from 21, and 21 minus 7 is 14, and there would be our measures. Let's look at an example going the opposite direction. So now we've got our dilation centered at O. Our scale factor is 1/2. It tells us that OA is a distance of 6, OB is a distance of 8, and AB is a distance of 4. So now, going through each of these examples, if we want to find A prime, B prime, so we want to find this distance right here, we know that it's going to be 1/2 the distance from A to B, which was 4. So if we take 1/2 multiplied by 4, that tells us that the distance for A prime, B prime is 2. Next, let's find O to B prime, which we know is going to be 1/2 the distance from O to B. The distance from O to B was 8, so if we take 1/2 multiplied by 8, that's 4. Next, if we want to find O to A prime, so we want this distance right here, we know that that's going to be half the distance from O to A, so that would be 1/2 of 6, and that ends up being 3. Next, if we want to find some more segments, if we wanted to find, let's say, A to A prime, so this distance right here, then we know the full distance from O to A is 6, and we also know that the distance from O to A prime that we just found, this distance right here, was 3. And so if we take 6 minus 3, that tells us that the missing distance that we wanted was 3. If we wanted to say find B to B prime, we know that the full distance from O to B is 8, and that O to B prime is 4. So taking 8 minus 4 tells us that B to B prime has a distance of 4. All right, now we get to finally see how proportions fit into dilations. So we're going to start by finding the scale factor, and then tell whether the dilation is a reduction or an enlargement. Then find the values of the variables that are in our diagram. So let's go ahead and do that. Taking a look at this first example, we've got our image, which is C to P prime, and then we've got our pre-image, which is from C to P. So to find our K value, we're going to take C to P prime divided by C to P. And so what we want to look for there is some values that match up. In this case, we could look at how 12.5 and 5 match up. So we know C to P prime over C to P is going to be larger than 1. That's going to tell us that this is an enlargement. Now the actual value for K then we can find by taking 12.5 divided by 5, which I'll go ahead and pull up the calculator so we can see what that is. So if we take 12.5 divided by 5, that tells us 2.5. If we want that as a fraction, we'll convert that. It tells us that 5 over 2 would be our K value. All right, so now let's solve for some variables. Let's solve for both X and for Y. So for X, so taking a look at X is going to be proportional to 8. So when we set up our proportion, we're going to say that X over 8 is proportional to another set of values that we know, which would be 12.5 over 5, because X is larger than 8 and 12.5 is larger than 5. Now we've got our equation set up where we can solve for X by doing our cross multiplication. So X multiplied by 5 is 5X, and 8 multiplied by 12.5 is 100. So then to solve for X, just divide each side by 5, and we get that X is equal to 20. Next, let's solve for Y. So Y is proportionate to 4 in the same way that 12.5 is proportional to 5. Again, we can solve this by cross multiplication. So taking Y multiplied by 5 is 5Y, and taking 4 multiplied by 12.5, we should get 50. From there, we just have to solve for Y, so divide each side by 5, and we should end up with Y being equal to 10. All right, one last example to look at for this section. So we've got our pre-image, which is from P to X, and then we've got our image, which is from X to, or from C to P prime. So we're going from C to P. So So this distance to C to P prime. So if you notice, the first segment I drew from C to P is larger than from C to P prime. In other words, I'm taking a larger size and making it smaller. That's what's going to tell me that this is a reduction. As for our k-value, we then need to find some values that we can compare. Well, we know that 7 and 12 are going to have to be proportionate to each other. So going from our pre-image, which was 12, because that was the larger image, divided by our image, which is 7, so the smaller, we get that k is actually going to be 7 over 12. I had those mixed around. So yeah, you want to go from your image to your pre-image. So that would be from 7 to 12. I just had those reversed. All right, so now what we can do is we can solve. This time we've only got one variable to solve for, which is x. We know that x has to be proportionate to 18 in the same way that 7 has to be proportionate to 12. So in order to solve this equation, we're again going to use cross multiplying to say that 12x is equal to 18 multiplied by 7, which 18 multiplied by 7 is going to be 126. So then to solve for x, just divide each side by 12, and we get x is equal to 10.5. All right, that's all we've got for this video's lesson. In a future lesson, we're going to see how we can use this idea of dilations to talk about what are called similar polygons and scale factors. Until then, have a good rest of your day.